And thank you for joining the public defense of Tinne Pauwels. And now we can all sit down. I will introduce the next. Ladies and gentlemen, dear colleagues, I hereby formally open this session and I welcome you all to the public defense of Tinne Pauwels. Tinne Pauwels has presented to the faculty the PhD thesis on the topic Companions of Massive Stars down to the Substellar Mass Regime, impartial fulfillment of the requirements for obtaining the PhD degree in science, astronomy, and astrophysics. Tinne Pauwels shall now publicly defend their PhD thesis. Tinne Pauwels, you are invited to give a presentation of about 45 minutes about your work. Afterwards, the examination committee will ask questions and discuss your work with you. And before the presentation, I would like to introduce the members of the examination committee. So they are two supervisors, Professor Hugo Sana and Dr. Madalena Richiani, and Professor Daniel Di Ferro, Professor Lino da Costa Pereira, and Professor Caitlin Crater, and they may join online, and Professor Olivia Epsil, and Professor Iran Beck, and he will join online. So, Tina, I now give you the floor to the presentation. Yeah. Thank you.
Can you all hear me okay? So hi everyone, and thank you so much for being here for my public PhD defense. So I will talk to you about my PhD project, which is on the topic of companions of massive stars down to the substellar mass regime. So let's start with a star that we all know, the star that's closest to us, which is the Sun. So the Sun has a mass of, by definition, 1 solar mass, which is about almost 2 times 10 to the power 30 kilograms. And the Sun is mostly made out of hydrogen with some helium and also a tiny fraction of metals, which is, for astronomers, basically anything that's not hydrogen or helium. And during its life, the Sun in its core will be hot enough to fuse hydrogen into helium. And this generates energy to not only prevent the star from collapsing under its own self-gravity, but also part of this energy is radiated away. And for the Sun, this radiation peaks in the visible. So this is the part of the electromagnetic spectrum that we can see. Now, the Sun can keep doing this for a total lifetime of around 10 billion years, and it's now around 4.6 billion years old, so about halfway through its life. Now, the Sun has many planets, and one of them is us, the Earth, and the Earth is at a distance from the Sun of 1 astronomical unit, or AU, and this is about 150 million kilometers. So at the end of its life, the Sun will become a white dwarf, which is basically the dense core of the star that is left, which can roughly have the size of the Earth. Now, next to the Sun, there exist also many other types of stars, and we can classify them by spectral type, which is a temperature-based classification. And with an effective temperature of around 5,800 Kelvin, the Sun is a G-type star. But solar-like stars are not the topic of this talk. I will be talking about massive stars. And these massive stars have spectral types O and early B-type stars, so they are very hot, very massive, and very bright. So massive stars are born with masses of at least 8 solar masses, so 8 times the mass of our Sun. And they are a lot brighter than the Sun, and the radiation that they emit actually peaks in the ultraviolet, so not in the visible like for the Sun, so they emit a lot more energetic radiation. And massive stars, they live for a lifetime of the order of millions of years. So even though they have a lot more fuel than stars like the Sun, they also burn through it a lot faster. So they really live like 1,000 times shorter than a star like the Sun. And then another thing about these massive stars is that they are rare. So less than 1% of all stars that are formed are born with a mass that's high enough to belong to this category of massive stars. Nevertheless, massive stars are very important, so they have a significant impact, for example, on star formation, because they emit very strong stellar winds, and also this ionizing radiation, and this can, for example, locally compress the gas and thereby trigger the formation of new stars, but it may also disperse the gas, and in that way suppress star formation. So it can both have positive and negative feedback. Massive stars also contribute to chemical enrichment of the universe. For example, they can complete the nuclear burning cycle all the way up to iron, which is something that a star like the Sun cannot do. And by also dispersing these elements into their surroundings through stellar wind, and also at the end of their life, they leave behind building blocks for new generations of stars and planets. So at the end of their life, massive stars may explode in a violent supernova, emitting a lot of energy into their surroundings. And unlike stars like the Sun, they will end their lives being a neutron star or a black hole, depending on the initial mass. So massive stars are also gravitational wave progenitors, for example, so very interesting objects. So understanding the birth, evolution, and death of massive stars is a fundamental goal in astronomy today. And I've highlighted this word birth because that's mostly what my research has been focusing on, and it's also something that for massive stars we don't really understand very well yet. So let's look a bit into the birth of stars. Let's try to form a stellar cluster. So star formation begins in a giant molecular cloud, and this is a cloud mostly made of atomic hydrogen. It's very cold, with temperatures of about 10 Kelvin, and dense, with densities on the order of 100 particles per cubic centimeter. Now, if we think about the air, for example, that we breathe, this has a density of about 10 to the power 19 particles per cubic centimeter. So dense is really relative. It's relative to the ISM that this cloud is dense. Now, at first, this cloud is still supported against self-gravity by its internal pressure. But at some point, a trigger from outside, for example, a supernova explosion nearby or a collision with another cloud, can actually trigger some overdensities in these clouds and can trigger thereby a gravitational collapse of this cloud. And this will create some denser clumps and filaments in the cloud, and then these may fragment and form dense cores inside this giant molecular cloud. And these cores are really the sites for star formation. Now, if we think about massive stars, we could imagine them forming in the highest density regions of this cloud, for example, where the accretion rates can be really high. Maybe their cores might also be more massive than lower mass stars. Well, lower mass stars will also form in this cluster, but they can also form in like the lower density parts, for example. So let's zoom into one of these cores. What can we see? Well, in the center of the core, you will have your forming star, and it will be surrounded by an accretion disk. And the star can accrete matter from this accretion disk, and in that way, it can become more massive. And there might also be some protostellar outflows, as you can see here. So then stars are accreting, they form. Important to know is massive stars will be less than 1% of all the stars that we form. So in order to form a massive star, you also form a lot of other lower mass stars. So then finally, all of the gas in this cluster will be dispersed, and the massive stars also really contribute to this. So they emit a lot of feedback. For example, this ionizing UV radiation, this can blow away the circumstellar gas and the disks. And also, after a couple of million years, some of the massive stars may already explode as supernovae, and this further contributes to the dispersal of this gas. Now, this is not what our final cluster will look like necessarily. Clusters are very dynamic, so they can still change a lot through interactions with other cluster members. So it will not be static and for all its lifetime look like this. So how are massive stars formed? So that's still an open question in astronomy today, because a comprehensive theory of massive star formation is still missing. And there are a couple of reasons why we don't know this very well yet. For example, massive stars have a very short formation timescale of the order of about 100,000 years. And within this time, they need to accumulate a lot of mass because they need to become very massive. And how exactly they accrete this mass is not really sure yet. So there are a couple of models, but there's not one single model that can explain all the observations that we see. Also, massive stars emit this strong UV radiation. So this actually blows away the circumstellar disk and the circumstellar material, also on timescales on the order of 100,000 years, or at least less than a million years. So forming a massive star is really a competition between having to accumulate a lot of mass, but also this pressure, this radiation pressure, trying to push away the gas. And then observing a forming massive star is also very challenging, because massive stars are usually found at large distances from us, which limits the resolution with which we can look at them. They're also rare, so this limits the amount of observable samples that we have. And during their entire formation time, they will be deeply embedded in a cloud of gas and dust. And this is really because massive stars, they already start burning hydrogen, by the time that they are still accreting mass. So it's you can't optically see them. An example is given in this image, for example, where in the center there is thought to be a forming massive star, but it's really hidden behind all of these gas and dust, so you can't see it. But if you look from top left to bottom right, there you can see where some light, where a powerful jet has actually cleared away some of the material. So, but one thing that we do know is that massive stars are not formed as single stars. So they are usually found with companions. And this can actually really help us in trying to constrain these massive star formation theories, because we know that any successful massive star formation theory should be able to explain the multiplicity properties or the companion properties that we see. So what do we mean if we say that massive stars are formed in binaries or with companions? So a binary is basically a system where two stars are moving around a common center of mass. And you can have two stars, which is a binary, but you can also have three stars in one system, or four stars, like a triple system or a quadruple system. And the number of companions that we find is referred to as the multiplicity. So observations of these multiplicity properties of massive stars are actually very important for constraining massive and multiple star formation theories. Now, multiplicity is not just something for massive stars. Many other stars are also formed in binary, and it actually seems that multiplicity increases with primary mass. So this is a figure that's based on observations where it shows you the multiplicity fraction on the y-axis. So that's basically the fraction of stars with a companion as a function of the primary mass. So then you can also see that, for example, for a one solar mass star, so a star like the sun, about 50% of them are found in binary systems, while if you look at massive stars, so O and B type stars, almost all of them are found in binaries. Okay, so let's take this binarity into account when forming our cluster. Where can we form binaries? Well, there are a couple of mechanisms, and one mechanism is core fragmentation. So this is really in the core that instead of one star, you will fragment into two, form two stars, and these can become gravitationally bound and also form a binary system. Another mechanism is disk fragmentation. So this is really then the disk around the star that can become gravitationally unstable and fragment, and these fragments may also form companions. And for massive stars, this disk can really be, so these are really found with very massive and large disks, and these are also very likely to become gravitationally unstable and fragment. And then a final mechanism to form binaries is capture. Capture is something that can also happen once the stars have already been formed. So this is really through dynamical interactions with other stars that you may capture a single star, for example, into a bound orbit. So I've already hinted at these dynamics, these dynamical interactions. They are also very important for binaries. So they really shape what our binary systems will look like over time. So for example, capture can lead to an increase in companions, but there's also the disruption of a binary system is possible. So interactions with other stars can also actually break apart your binary if it's not very tightly bound. And then something else that can happen is migration. So in migration, stars are formed further away from each other, but then also through interaction, for example, with other stars or with gas or disks, you can actually move your companion to a tighter orbit. So companion populations can change over time. And there are a couple of questions related to this that I have been trying to answer in my thesis. So the first one is, how does the environment shape massive star multiplicity properties? So this really points to, for example, the density of the environment. In very dense environments, you will have a lot more interactions with other stars. And how do companion populations of massive stars evolve over time? So how do these dynamical interactions actually shape what our binary systems will look like? And then there's another question that I have been trying to answer. Something that we don't really know is whether low mass companions can exist around massive stars. And this is also, theoretically, it's quite challenging to form a low mass companion around a massive star because these massive stars emit this very intense UV radiation. This significantly shortens the disk lifetime, for example, and thereby limiting also the time that companions have to form in the disk. And this photoevaporation, this intense UV radiation has even been seen to photoevaporate the disks of nearby stars. So this really creates a very harsh environment around a massive star to be able to get such a low mass fragment to survive and become a star. So it's a harsh environment to form low-mass stellar and substellar companions. But so substellar, that was also part of my title. What do we actually mean by that? So we all know stars. I just discussed them in the beginning. There's also planets, which have lower masses than stars. But in between stars and planets, we have brown dwarfs. And basically anything that has a mass below that of a star is what we call substellar. Now, there's a minimum mass to be a star, which is about 0.08 solar masses, because if you don't have this mass, you would never reach the temperatures in your core hot enough to do this hydrogen burning. So this is what separates stars from brown dwarfs. Now, brown dwarfs cannot do hydrogen burning. They can still do some deuterium burning for a limited amount of time, and this is what still separates them from planets. But if we talk about substellar, I mostly mean brown dwarfs when I will talk about this in this talk. So also observationally, it's actually very challenging to find these low mass companions around massive stars, because looking back to this figure, this was actually created using observations that are only complete for companions that have masses higher than 1/10 of that of the primary star. So that means that for a star with a mass of 10 solar masses, you're only including companions that are 1 solar mass or above. And it's really due to instrumental contrast limits that it's just so hard to find them, because massive stars, they can be even 1,000,000 times brighter than a sun-like star. So they're very, very bright, and it's often compared to trying to find a firefly next to a lighthouse. So and finding this firefly, this tiny companion, is just very difficult if the massive star overshines everything. So if we want to answer these questions, what we need are observational constraints. So now let's look at these different binary formation mechanisms and look at in which separation ranges these are expected to create companions. So there's this core fragmentation mechanism, and in these mechanisms, it's expected to create initially more widely separated systems, so a couple of hundreds AU away or even further. But these companions can actually migrate inwards on short timescales of the order of about 100,000 years. Then there's also disk fragmentation. This can basically create companions over the entire range of the disk. And for massive stars, this disk can really be up to a couple of thousands AU even. And then capture is mostly expected to create more widely separated systems. Now, if we want to probe this entire separation range of companions around massive stars with observational techniques, we actually need to combine multiple observing techniques. So it's not possible to see all of them with one technique. So I will not go into the details of this, but I will just show you them so you know that they exist. So for close companions, spectroscopy is often used. For intermediate companions, there is interferometry. That's a very important technique. And then as you go to wider separations, you can start using direct imaging techniques. And direct imaging is really, it's basically taking a picture of your star, taking a direct image of your star. And the technique that I've been using in my thesis is one of these direct imaging techniques. So it's high contrast imaging with coronagraphy. So we're probing more widely separated binary systems here, a couple of hundreds AU up to thousands of AU, but we can reach very high brightness differences. So very high contrast, really allowing us to probe these low mass companions around massive stars. So we do this high contrast imaging with SPHERE, which is a high contrast imaging instrument on the Very Large Telescope, or VLT, in Chile. And SPHERE stands for Spectropolarimetric High Contrast Exoplanet Research. So as the name suggests, it's actually mostly used to find exoplanets around solar-like stars, but we can also scale this up in brightness and thus mass, and try to find low mass, potentially even substellar companions around massive stars. So what we do with SPHERE is that we take a direct image of the star in the infrared. But so these low mass companions, how can we actually find them? Because it's really this tiny firefly that we want to find next to our very bright lighthouse. If we could turn the light of the lighthouse off, that would be nice, but we can't do that with a massive star. What we can do is try to put something in front of it that blocks the light of our massive star, and then our tiny firefly, our small companion, can become visible. And this is actually what we do. So we use a coronagraph, which is really a small device that's put in the path of the telescope that blocks the light of the central massive star. And then since the companion light comes in at an angle, it misses the coronagraphic mask, and we can see it on the detector. So this really allows us to answer this question of low mass companions around massive stars. So we have several samples for which we have obtained sphere data. So it's all massive stars that are located in different regions on the sky, different environments. And so we have 9 massive stars in M17, which is the youngest sample for which we have data. Then a sample of 39 stars in the Carina region, which is slightly older, between 2 and 4 million years. And a sample of 19 stars in the Scorpius OB1 association, which is the oldest region for which we have data. And because we really have this gradient with age, we can try to answer this question about how companion populations evolve over time. And then we also have a sample of 25 stars that are in low density regions. So these are really regions all over, so that are like very loose OB associations, maybe some stars that are part of the field. And this really allows us to test how the environment shapes multiplicity properties. So what the effect is of having a denser cluster or a very low density environment. Okay, but what binary separations can we actually find with spheres? So how big is this picture that we are taking? And this is referred to as the field of view, and it's expressed in arc seconds. So that's literally an angle on the sky. And for a sphere, that's about 12 by 12 arc seconds. To give you a point of reference, the moon is about 1,800 arc seconds in diameter. So it's really a tiny fraction of that we are looking at on the sky. But what does this translate to in terms of actual binary separations? Well, that will depend on the distance. So let's say that we have a binary system that's at a certain distance from us. Here you can see it's a triple system, and we have one companion that actually falls inside our field of view, but another one that may be further away falls outside of the field of view. But if we would have this exact triple system, but it's further away from us, then suddenly you can see that our further companion actually falls within the field of view. So we can probe wider separations if our star is further away. Now, important, we also, of course, have this corona graph. And this has a diameter of around 0.3 arc seconds, where we can't see anything. So that also means that if your system is too far away, you will be missing a lot of the closer companions. So to give you some actual numbers, at typical massive star distances, for example, at 1.5 kiloparsec, which is about 5,000 light years, which is a distance some of you might be more familiar with. So that's the distance that light travels in a year. There we can find binary separations between 225 and 9,000 AU, so widely separated systems. But if we have a star at 2.5 kiloparsec, or about 8,000 light years, then we can only start finding companions from 375 AU, but up to 15,000 AU. So what does this sphere data actually look like? So this is an image that was taken with one of the science instruments of sphere, the IRDIS, and it has a field of view of 12 by 12 arc seconds, and we get these images in 2 different wavelength bands. So that means that we get information about the brightness of the sources that we detect at 2 different wavelengths. Now, at the center of this image, there we will have the massive star, which is hidden behind the corona graph. Now, we also use a second science instrument from sphere, which is called the IFS, and it's a much smaller field of view of about 1.7 by 1.7 arc seconds. But for these images, we get brightness information in 39 different wavelength bands. And this really allows us to extract a spectrum, a low resolution spectrum for the star that we can compare to models. And this allows us to infer some of the fundamental properties of the companion, for example, a mass. So let's look into some data analysis of sphere. So our data is actually not just one image, but we will have a stack of images. And this is very helpful because the images can still contain some noise that we call speckles, which we can confuse with companions. But they will behave differently from true sources in all of these images. And then by combining all of these images in a special way that we call angular or spectral differential imaging, we can actually remove or reduce the noise and enhance also the signal of true sources. So there we do this and we get our post-processed image. Now we also have, of course, this IFS field of view, where in this case you can see we detected a source, a companion maybe. And because we can now extract this low resolution spectrum for it, we can also characterize this companion. So this is what such a spectrum looks like. So it's the brightness as a function of the wavelength. We can compare this with models. And in this way, we found that this companion has a mass between 0.1 and 0.25 solar masses. And it's at a separation of about 540 AU. So it's a very low mass companion. Now, looking back to this first image, you can see that I circled a lot of things there. So that are all sources that we detected. And So it's a lot, but it's important to realize that not all of these sources will be bound companions to the central star. So in fact, most of the sources are there due to background contamination, and really distinguishing true companions from these background sources, that's an essential point in any high contrast imaging survey. So how can we do that? Well, maybe the most elegant way is to look at the orbital motion of your companion. Because of course your companion will over time be moving around the central star, while background sources will not do any of that. This of course requires additional data, but more importantly, these white binaries that we are probing, they can actually have periods of over 1,000 years. So we can only probe a very tiny fraction of this orbit, and in order to see this curvature of the orbit, you need very, very precise measurements of the positions of your companion. And with SPHERE, this is something that we cannot do over only a couple of years. You would really have to wait decades with SPHERE. Now, something else that we can do is not look at the orbital motion, but look at the proper motion of stars, because stars are moving relative to us, but also relative to each other. And a companion of a star should, of course, be moving with the central star, so it cannot move differently. So this is also another way in which we can distinguish these two populations. Now, of course, this also still requires additional data. You still have to wait a couple of years for the stars to have moved enough to detect these differences. And this is not something that we always have. In fact, most of the time we don't have it. So can we not do anything? Luckily, we still can do something, but we have to approach it in a statistical way. So we can calculate the probability that a certain source that we detect is a background source. So let's say we detected this source in our SPHERE field of view. What we then need is information about the density of background sources in this local region around this massive star. So we can get this information from actually observed catalogs, like 2MASS, for example, but we can also get it from models like the Besançon model of the galaxy. And we only take into account sources that are at least as bright as this source that we detected in our SPHERE field of view. And then we randomly divide all of these background sources over our SPHERE image, and then we can calculate the probability of finding at least one background source within the separation of our source that we detected. And this is referred to as the spurious association probability. So that is the probability that a source is a background object. So the probability that it's not a companion. Okay. Now let's look into some actual results. So one of the regions that I studied in my thesis, which was actually my first project, is the Scorpius OB1 association. It's an active star-forming region between 6 and 8 million years old, and it's at a distance from us of 1.5 kiloparsec, meaning that we are probing companions between 225 and 9,000 AU. And we have a sample of in total 19 OB stars with SPHERE. So then this is the result for that sample. So these are all of the sources that we detected around all of these 19 stars that are part of this sample. And on the y-axis, it's showing you the brightness of the source, and on the x-axis, the separation of each source with respect to its own central star. And then all of the different colors in these plots, those are the spurious association probabilities, so the probability that it's not a companion. So the lower this probability, the higher the chance that you will have a true companion. And then you can see that, for example, like very close to the central star or very bright sources, those are sources that are more likely to be companions. While if you look at sources that are very faint or further away from the central star, those are much more likely to be background sources. Now, in this diagram, we can also plot the region where we would expect to find brown dwarfs and planets, just based on the brightness. And you can see that we are really probing this brown dwarf mass regime around massive stars with SPHERE. Not yet the exoplanets. We don't have contrast enough to do that. But so interestingly, we also have some brown dwarf candidate companions here closer to the star. But as you can see also, the spurious association probability in this faint brightness regime is actually, they're actually very high. So in order to be able to confirm some of these brown dwarf companions, we really would like to have another way, like another observation to trace their proper motion or maybe even their orbital motion. So let's look into some of the statistics of this sample. So for this sample, we found that the fraction of stars with a companion, or also called multiplicity fraction, is 89%. And we found an average number of companions per star, which is equal to 3.5. So this would really mean that all of these stars are not just found in binaries or triple systems, but they're even found with between 3 and 4 companions. However, an important side note here is that we did not yet take into account any of the biases that might be present in this data of sphere. And it's actually very important that we correct for this. So let's look into these biases. So one obvious bias is, of course, that we are dealing with these two populations of sources. So we have background sources and true companions, and we need to in some way take into account this uncertainty that we don't really know which are true companions and which are background sources. Then also there might be some closer companions that we might be missing. There might be even fainter companions, although we are already probing quite faint for almost all of the stars. But also all of these different samples that we have, they might be, there are different distances from us. So that also means that if we want to compare, for example, the Scorpius OB1 region with Carina or M17, we need to correct for the fact that we are probing different binary separations in each of these samples. And then finally, our data is also likely incomplete due to projection effects. And what do I mean by that? So this is really how this binary orbit is projected onto the sky. So your binary, it can be moving like this with respect to us. It can also be moving like this or like this. And actually, depending on the actual parameters of your binary system, your companion might still be spending a lot of time or a significant amount of time behind the coronagraph, as you can see here, for example. So this shows you the projected a histogram of the projected separations, where I've put here the coronagraph, so you can see that a binary with a semi-major axis of 250 AU with these specific parameters can still spend a lot of time behind the coronagraph. And then we might miss it, depending on when we observe it. So we want to correct for all of these biases. And what we actually want to get out of this is the intrinsic number of companions in a specific separation range, which we here chose to be 250 to 5,000 AU. So intrinsic meaning the true number of companions corrected for the fact that we also have these projection effects, for example. And we would also like to get some information on the mass distribution of these companions. So we do that by modeling it as the mass as a power law, and then we try to get out this gamma exponent. And what I want you to remember is that a low gamma means that our companions are more low mass, while a high gamma would mean that companions are more high mass. So in order to do this bias correction, we do that in a Bayesian way, where we and basically what we do there is that we model the companion and background populations separately, and then we combine them. We correct also for these projection effects of binaries and for the detection limits, and then we create a model that we can actually compare directly to our data. And in this way, we determine the most likely number of companions in our data and the most likely mass exponent gamma. So the following results are bias corrected, and they include only companions in this separation range 250 to 5,000 AU that have a mass above 0.1 solar mass. So I'm not yet including any substellar companions. So let's look into some results. So let's try to answer some of these questions that we asked in the beginning. So how does the environment shape multiplicity properties? Well, then we can compare these low density environments to our denser clusters like Carina and M17. And we will look specifically at the mass distribution here. So then you can see that we actually found a lower mass exponent in this low density region than in these cluster regions, meaning that companions are relatively more low mass in this region. So why could this be the case? Well, of course, in these denser clusters, we have more dynamical interactions, so more interactions with other stars. And this could actually mean that some of these lower mass companions, which are usually less tightly bound to your central star than a more massive companion, they are just more easily disrupted. So in this scenario, low mass companions would form in all regions, but they don't survive in dense clusters. Now, of course, there's also another possibility. So it might also be that low mass companions simply form more often in low density regions. And then it really points to a difference in the formation physics. For example, I'm thinking about differences in the feedback that might lead to differences in fragmentation, things like that. So then how do companion populations evolve with time? In order to answer this question, we can look at our samples in which we have this age gradient, so M17, Carina, and Scorpius OB1, where M17 is the youngest region. And then we can look at the average number of companions that we detected in each of these regions. So then you can see that for M17, we actually found more white companions than in these older regions. So interestingly, also a previous study found that close companions are missing in M17. But so the fact that we find more white companions in this young region, while the close companions are still missing, and in older regions you detect less white companions, could actually mean that there is migration going on. So this could point to a migration scenario for the formation of binaries in M17. So finally, let's look into some of these low mass companions around massive stars. So we detected actually multiple candidate low mass companions in the IFS field of view of several massive stars in Scorpius OB1 and also in the M17 region. And interestingly, two massive stars have candidate companions that would be in the brown dwarf mass regime. So these would be super interesting to follow up. One star even has two brown dwarf candidate companions, but as you can see, the spurious association probabilities are quite high. So in order to really be sure that these are companions, we would have to obtain some follow-up observations and prove that they are companions in this way. Sadly, we didn't get them yet for these stars, but we did get follow-up observations for some of the other low-mass companions around massive stars. So these are low-mass companions, but still within the stellar mass regime, so with masses below 0.3 solar masses. Now, with these follow-up observations, what we can do is that we can trace the proper motion of these sources and test if they are co-moving with the central star or not. And so we had observations for 3 of them, and we found actually that 2 of these companions are co-moving with their star, which gives them a very high probability of being true bound companions. So we found one B 0.5 type star, so that's a central star with a 0.3 solar mass companion, and an O 9.7 type star with a 0.13 solar mass companion. And these companions are separated by, in this case, around 800 AU, and in the other case, around 1,000 AU. So far away from their star, but really very, very low masses. Now, how did these companions form? So that's still very uncertain, but we can look at all of these different formation mechanisms of binaries that we discussed in the beginning to see whether these could likely have formed our systems or not. So disk fragmentation, that could be a possibility maybe, but simulations of specifically disk fragmentation around massive stars actually predict higher fragment masses on the order of a solar mass. Some lower fragments also formed in these simulations, but they simply didn't survive. And also there's still this question of whether low mass companions can survive this UV radiation. Now, from these simulations, actually, the fate of the fragments is still uncertain because these simulations are run for like a lifetime of a time of around 15,000 years, which is only a fraction of the total formation time of a massive star. So these fragments could still be destroyed or even accreted by the central star. And the limitation here is really the computational cost. So it's just very computationally expensive to run these simulations. So it's very hard to do it for longer times. Another mechanism to form binaries is core fragmentation. But in core fragmentation, you form both stars in the same core. So that also means that both stars can accrete from the same mass reservoir. And this would make like forming one very massive star with one low mass companion unlikely. However, some very recent simulations have actually shown that it might be possible. So these simulations even came out after I had already submitted my thesis, so they're very, very recent. But actually, they found a system which is very similar to the systems that we observe. So they found an inner binary of 12.5 solar masses in their simulations with a tertiary companion that has a mass of 0.1 solar mass at 2,300 AU. So this is really very similar. And so what happens is that basically you first have the formation of the inner binary, and then after only about a couple of 10,000 years later, you will suddenly form a tertiary companion within the same core. And this tertiary companion can get gravitationally bound to this inner binary and can still, like while it's moving towards there, accrete some mass from the disk of of these other stars. But because these stars are already forming for a long time, their feedback will actually disperse the disk quite rapidly. And it also means that your companion doesn't have a lot of time to accrete more mass. So that's why it remains low mass. And then finally, another mechanism to form binaries is capture. And this we cannot really distinguish from an in situ formation mechanism based on just one observation. So, but what we can do is we can increase our sample of observations and then compare it to simulations. Because from simulations, what we can get is the expected occurrence of such captured companions. For example, Parker et al. In 2022 found that the expected occurrence of captured substellar companions around massive stars is about once per association. So if we are able to confirm a lot more of these systems, then that means that another mechanism should also be at play and that capture cannot explain all of them. Okay, that brings me to the end of this presentation. So we looked at the effect of the environment and we found more low mass companions in low density regions, potentially due to dynamical interactions, so due to disruption of low mass companions in these dense environments. We also looked at the evolution of companion populations over time, and there we found more wide binaries in the young cluster M17, potentially pointing to such a migration scenario for the formation of binaries there. And we also found several low-mass substellar companions or candidate companions around O and early B-type stars, but their formation is still very uncertain. So then in the future, what are some things to be excited about? So on the observational side, there is Gravity Plus now. And Gravity Plus would actually be able to trace the orbital motion of our companions within only a few years of observation. So it's so precise that we'll be able to do that, which would be very interesting for follow-up of these brown dwarf companions. Also, the ELT is coming up. That's the extremely large telescope. And there the METIS instrument will be able to probe even closer and fainter sources than what we can do with SPHERE. So this could potentially even allow us to start finding exoplanets around massive stars, although I think it will be important to find a way to limit our background contamination first. And then on the theory side, for simulations, it will be very nice that even in the future we can get some simulations that actually predict observable companion properties like separation and mass distributions that we can directly compare to our observations. And I think this will really be essential to constrain massive multiple star formation. Thank you.
Hi, everyone. I didn't hear what was said. Sorry.
Hello, Professor Beek. It's
Yes.
your time for asking questions.
Okay, thank you very much. Dear Tinne, first I would like to actually congratulate you with your amazing talk about your thesis and also about your thesis itself. I think you have done an amazing work, which is also very important. You've made a lot of progress and important to understand how these low mass companions actually form and try to understand how they form. And with all these new observations you have presented, I think we have done a major step forward. So I think, I would like to congratulate you with that.
Thank you.
I obviously have some questions, and yeah, you in your presentation you've talked a lot about the different mechanisms. So could you explain a little bit more about this capturing mechanism you are explaining? Like, because you say sometimes it can disrupt, sometimes you can capture. So what kind of relative velocities and parameters would you need? And yeah.
So indeed, in order to capture a star, what you need is a mechanism to dissipate the energy, because a binary is actually at a lower, like a bound binary is at a lower energy than just two unbound stars. So you need the kinetic energy that these stars have needs to become low enough so that the gravitational energy that binds them is actually higher. Now, so what can happen is, for example, that you have a binary system with another star, and then you can capture the star and maybe eject one of the stars of the binary system to capture the other stars. You can also have a binary-binary system where you capture one of the stars of the binary system into a triple system and the other star is ejected away, something like that. So it can, then you have the other star that is carrying away this excess of energy. What can also happen, where you don't necessarily need another object, is if there's still gas around or disks, then you can use these disks or the gas to dissipate the energy. And typical velocities that we are thinking about is in an OB association, for example, the velocity dispersion would be about 1 kilometer per second. So that's more or less defining the kinetic energy of your stars.
Okay, thank you. And yeah, you've also talked a lot about also especially in your paper in section 3, well also 5, where you discuss the background contamination. And indeed, that is a major problem. And you use these Besançon models. So I was wondering, like, did you try to tune them? Like, are there possibilities in getting different models, like using a different extinction law, using different cell populations, or is this a fixed model you have and you cannot change it?
That's a good question. I think for the Besançon model, it's mostly fixed. You can change some things, but it's mostly related to really the parameters that you want to get out of the simulation. So you can, for example, change the distance up to which you want to run the simulation. You can change what kind of magnitudes you want to get out of this, in which bands. You can choose whether you want to include also proper motion or not, things like that. I'm not sure if there's a lot that you can choose yourself with the Besançon model in terms of which extinction law you're using. In any case, I didn't play around with it.
No. So it's hard to get an idea on how systematic what the systematic uncertainties coming from this model, like what effect that would have on your probabilities.
If there's like some systematics that would be like wrong in the simulation, or what is
yes, well, I mean, not like things we don't know.
No. Yes, but actually, I think the Besançon model has also been tested against, for example, Gaia data, and that's also something that we did, especially for this background contamination. We really compared the Besançon model also to observed catalogs like 2MASS, VVV, and Gaia, and we actually found that these results are very consistent, at least up to the magnitudes where these catalogs can see, because they just can't see faint enough, so there we really need this Besançon model to go up to the faint magnitudes.
Yeah, okay. Thank you. Right, so then another issue is, which I think is more important for the denser clusters, is that you will have, even in the cluster, you will have chance alignments, right? You will, I mean, the cluster is a 3D entity, so you will have also, let's say, background which is not in these models. Do you think there is a way to constrain this?
Yes, definitely there could be a way to constrain this if you know the density of your cluster itself. So I think for loose OB associations like Scorpius OB1, this shouldn't really be a problem. I think we don't really expect to find a lot of chance alignments from the cluster itself. But for really dense clusters, like for example, Trampler 14, I didn't include it in this talk, but it's also a cluster that was looked at with Sphere. There you really have densities on the order of more than 10,000 stars per cubic parsec. So then really you will also have a lot of cluster members in your sphere field of view. And I think you can correct for this in the same way that we are taking into account the density from these catalogs, that we can take into account the density of the cluster itself also as an extra factor. And calculate the spurious association probability from that.
Yeah, okay, thank you. Then I wanted to talk about this fragmentation formation channel. right. So the simulation seems to have difficulties in actually forming low mass companions or not forming them at all. So what would you now with your results you have? What would you tell these the modelers? One of the things you mentioned already was like it would be great if they could run them longer.
Yeah.
But like, what other effects could be important which they are still missing? Like, especially example when you're looking at these denser clusters, like when things are forming close to each other, there are multiple O stars forming.
Yes, okay. Yes, so one thing that this simulation, for example, did that it really looked at the formation of one massive star. So it's not really taking into account any feedback of other stars. It is including feedback from the massive star where it's forming, but yeah, indeed not other stars. So that's something that's not taken into account, which could be very interesting to look at, especially for denser clusters where this might be important. Yeah, then I think it would be, yeah, so maybe that would be interesting. And then, of course, also running them longer so we can see which fragments in the end turn out to be really companions and which ones are still accreted by the star or just destroyed in the disk, things like that.
So yeah, because you said these simulations that these lower mass fragments are destroyed, but could they then still be formed again? Because if they're destroyed, they're gone, and whether you run it longer or not wouldn't make any difference, right?
Well, I don't know, because you also don't know yet the final mass that your companions will end up with. If they're still in a disk, they might still be accreting from the disk, or some photoevaporation can maybe still remove some material of these fragments. So I think it would still be interesting to look at what final companion masses you end up with.
Yeah, okay. One last question. It's actually about this slide you have now, although it's not. It's about like space-based observations, right?
Yeah.
And you are obviously fighting a lot with the Earth atmosphere. That's part of the, that's why you're using sphere to use this extreme AO. And so, would using space instrumentation not help with this? That you were able to find these companions easier because it's more stable?
Yes, definitely. Space helps a lot, but it mostly helps actually for the contrast that you can reach, because so you don't have the atmosphere anymore, and then you can really, really probe to very faint magnitudes. For example, JWST is really good at that, also getting really good photometric precision. A problem still at the moment for our observation specifically is that the inner working angle of JWST, so the closest that we can see, is too far out for us. So especially for these brown dwarf candidates, they're really at the edge of what JWST can do. That doesn't mean that there are not exciting future missions that are coming up. For example, the HWO, the Habitable Worlds Observatory, where I think the inner working angle will be a lot better, the contrast will be even better, and we will also have brightness information over the UV, visible, and infrared, which would really also allow for a good characterization of these companions.
Okay, thank you very much for your answers. I have no further questions.
Thank you.
Thank you for your questions. Next is Professor Epsil.
So I like to join Ian in congratulating you on your very nice presentation, but not only presentation, for the whole work that you've done and this very nice manuscript that I enjoyed a lot reading. So yeah, really congrats on the very nice piece of work. I know I'm not supposed to ask very technical questions, but I still want to ask one because I'm here for that. But it's not too technical. So it's just a question about how you process the data. So you didn't talk about that today for obvious reasons.
Yeah.
But I would like you to still say a few words about the importance of principal component analysis, which is the tool of choice that you have used for processing your data. So can you say a few words of how it works and why it's so important to your field?
Okay, so it's principal component analysis. Okay, I have to think a bit about where to start. So we use this so I very briefly mentioned this angular and spectral differential imaging. So basically what we do is that we combine these images in a special way, but we want to remove the noise. And the way in which we remove this noise, that's actually something that PCA, principal component analysis, helps us with. So in order to remove the noise, we first need to get a good model of the noise that we can remove. And the way in which we construct it, so you could also just take the mean of all of the images that you have, and then you remove that as the noise. But principal component analysis actually goes a step further. So if you have your stack of images, it will basically, so the first principal component will have capture the most variance of all of your images, and you have a second principal component which captures also the second most variance, and then you go on. So you basically split your image into multiple principal components, and then we can decide basically so how many principal components that we want to use to create this reference PSF. We can just use one principal component, which is mostly very similar to just taking the mean of all of these images, and then we remove that. But you can also include like another principal component and more, and we can really see, like, test which number of principal components is the best. So the one that really maximizes our signal to noise for our companions. So for very faint companions, for example, that can really help in finding the best match that really maximizes the signal to noise.
Thank you. So now more general questions. So you said that you didn't have a sensitivity to detect planets around massive stars, but what do we know in general about planets around massive stars? So do we know whether they form? Do we know whether they survive the end of the life of these stars?
So as far as I know, there's not a lot that we know yet, because we haven't been able to find them yet. Also, whether forming a planet around a massive star is possible even is very uncertain, because these disks really don't live long. And of course, there's two mechanisms to form planets. You can do it through these gravitational instabilities in the disk, which is quite fast, so then it can still happen over the disk lifetime of a massive star. But for example, this core accretion mechanism to create planets, I think this takes timescales on the order of millions of years, which is just not possible with the lifetime of the disk that we have around the massive star. And then indeed, whether this can serve, these planets could be able to survive the end of the lives of massive stars, I don't think so.
Okay. All right. So about the way to test whether a companion that you find is gravitationally bound to the star or not. So you said that you need to repeat the observation about after a certain amount of time to see whether they are co-moving. But what are the odds that the stars are just in the same cluster and moving in the same direction? And is there a way for you to know whether it's just a chance that it's moving in the same direction as the star that you're observing, or whether it's gravitationally bound? So is there another way for you to tell whether it's actually truly bound to the star or not?
So if you just look at the proper motion, there's of course indeed always a chance that it could just be a cluster member, because you're not tracing the orbital motion. That's the only way, I think, to know for sure. But that doesn't mean that we cannot calculate some probabilities to see how likely it is that your co-moving source would be just a cluster member. And that's something that we didn't do, but I know that they did this for another survey, the BEAST survey, which studied the multiplicity of B-type stars in the Scorpius-Centaurus region, which is also sort of a loose association like our OB associations. And there they actually found that the probability of having a cluster member that is co-moving instead of a bound companion is actually really low, just because the chance of having like this chance alignment with a cluster member in your sphere field of view is very low.
Okay, but if you don't want to wait too long to make this this test, is there a way for you to lift this ambiguity with astrometry using either gravity or Gaia? What do you think would be the best way to do that?
Oh, definitely gravity plus, I think, because then you get super, super precise measurements of your position. And then you could really also start tracing this orbital curvature. So you just have to prove that your source is not moving on a straight line, but it's moving on a curve.
Okay.
So.
Okay, thank you. So in this slide, you say that you would like the models to make prediction on observables that you can test with your observations. So what you've been talking about mostly is occurrence rates, which you have been testing, but there are other things that you can test, like mass distribution or other things. Based on, the models that we have access to right now, what do you think would be the most important parameter that you could test with observations? Is it mass distribution? Is it occurrence rate? Is it something else?
Well, that's a good question. So I think, all of them will be important, and we need to take all of it into account. But for example, if all of these different mechanisms like core fragmentation or disk fragmentation or capture, they might also be expected to create different mass distributions or different separation distributions, especially of companions around your star. And I think this would be really interesting to really look at the distributions indeed of the companions that we see and be able to compare this to really each mechanism like separately and see if we can try to find out which mechanism is actually the dominant one, for example, in creating these binaries. So I think, the distribution of companions maybe, but although occurrence rate is also important, maybe more important for capture.
What about eccentricity? If you might be able to measure them, do you think that could be a good one? Or
yes, definitely. I think that.
How do you think that different mechanisms would modify the eccentricity distribution?
Oh, that's a good question. I think for capture, you will have mostly highly eccentric orbits. For disk fragmentation, it will be maybe more like aligned with the disk. For core fragmentation, I think it's also usually quite chaotic. So I guess you can also be expected to have some eccentricity or like random eccentricities. Although I think also interactions with other stars can still change all of this. So that would also be important to take into account.
Okay, so maybe a last question on my side. So you discussed the distribution of companions versus age, and in terms of wide separation and short separation companions. And so you showed that the ratio of wide separation to low separation companion might change over age, and you said that migration could be a mechanism to explain that. I was wondering whether gravitational interactions could also explain this behavior, or if it's really only migration that could explain it. I mean, if you have interactions in a cluster, the ejections, could they also produce closer in companions, or is it mostly ejections that you expect?
So you mean like still having migration, but due to interaction with other cluster members? I think that's definitely possible because we really need this migration to also happen over the timescale of about 1 or 2 million years, because at 2 million years already we see much less wide companions. And I think indeed like interactions with other stars can harden your system, which is also a sort of migration if your binary is hard, meaning that the binding energy is larger than the average kinetic energy of the cluster. But that will also mean that if you have a lot of interactions, you might also be disrupting some binaries, the ones that are more softly bound. But I think this is definitely a mechanism that could be causing this migration that we see.
Okay, thank you.
Congratulations, it's really nice work, really nice presentation. Also, I should apologize that I couldn't make it to the first events. I had this meeting abroad that I really couldn't miss, and it was really overlapping, so I'm not even online. I don't think I was missed because I'm anyway not an astronomer. I'm a condensed matter physicist. And so my questions now will also come from that perspective. Apologies in advance. I try to find links in the physics of the aggregation and so on, and there are, but maybe they would require maybe too much condensed matter physics knowledge, so it would also not be very nice for me. So I went into the instrumentation, which is also not maybe the best, but I will try. But so if you have no idea what I'm talking about, just say that, and I'll go to the next one, because the chances are very high, and it's not your fault. It's my fault. It's not you. It's me. So you mentioned the issue with the more massive stars are much brighter than the fainter companions, but I suppose that the spectra are very different. That the more massive stars will have very different spectra, and so is this this is a problem we also have in other fields, like in some solid state systems. Is this the reason why the instruments are specifically based on infrared region of the spectrum?
So infrared is in any case a good place indeed to look for companions around massive stars, because massive stars are mostly very, very bright in the visible and in the UV, but this brightness goes down actually by a lot by the time that you reach the infrared. And of course, the brightness of solar-like stars also goes down towards the infrared, but actually the difference in brightness between your star, your massive star, and your fainter companion in the infrared will be a lot less than what you would have if you would be looking in the visible, for example. So indeed, I think that's
okay.
Then
I get it. We play similar tricks. So a faint is always faint, but the ratio.
Yeah, but it will also
yeah.
the fainter will peak more towards the infrared. So
yeah. So that's unfortunate, because then I'll continue my questions about in that axis. So then you have an infrared detector, semiconductor, somewhere in the instrument. Do you have any idea what I'm talking about? So what material what semiconductor it would be, or now this is going too far?
No, this is going too far from my knowledge.
Because I suppose not silicon, and then I wasn't sure would it be mercury, cadmium telluride, or an InGas, but that's
the person next to you might know this.
Then I'll go to another one, but if you have no idea, it's also fine. Because you mentioned something about adaptive optics.
Mm-hmm.
Do you have any idea how that works in practice?
Yes, I have a little bit of an idea, maybe not very detailed, but so these adaptive optics are really important because we have the Earth's atmosphere, and this can be turbulent in some regions. This can actually delay like parts of your wavefront, for example, and then it will like reach a detector not exactly in the place where you want it to be, and this is
the phase you mentioned.
The phase, yes, the phase. Sorry, yeah. So. Then this adaptive optics, basically how it works is that a deformable mirror is used, which can actually correct, like put the corrections of like what you need to do to your wavefront. So first you measure it, and then it goes to some sort of a computer, I think, and then it gives some feedback to the deformable mirror. And then basically your light reflects off of it, and you get your corrected wavefront that moves further to the telescope. So I think that's in very basic terms how it works.
Do you have any idea how the mirror does that? It's okay. It's solid state physics. So there's some you guys benefit from some of our stuff. Then I'll go back to maybe something that is more comfortable again, and then you can relax. So you use Bayesian statistics to overcome observational biases. We all do that. So in condensed matter, we all do it. Everyone is doing that. Maybe you mentioned it, but I didn't jump out in the thesis. What are the main observational biases in your kind of astronomical data?
So the main observational biases that we have are, there's multiple. I can maybe show this slide again. Yeah. So basically it's all of these, but mostly, I think what you want to correct for, if you're doing a bias correction, is mostly this incompleteness effects due to projection of binary systems, but also due to your detection limits, which might also be changing across separation. I think for us it was also really important to do this, to be able to compare with samples at other distances, to make sure that we're really probing the same physical separation ranges around all of our companions, both in separation and in mass. And then we, of course, also have these two populations of background sources and true companions, which is a big bias. But
Okay. And then finally, and this is nowadays, I always end my questions on machine learning. It's very popular. So you didn't use any, and that's fine. I also don't use much. But do you see potential for machine learning on some aspects of your work? On, I suppose, on the data reduction, on the data analysis, and I suppose about the detection of the faint companions versus. Is this something that people are doing or might be doing?
Oh, that's a good question. I actually don't know if people in the high contrast imaging community are really using this to do data analysis. I think maybe, also in the bias correction, it could help us somehow. I'm not actually sure.
Okay, thank you very much.
Hi, Tinne. Congratulations on the very nice thesis and amazing presentation. It was very good and very clear. I have a few questions. I will start by a general question. So you analyze association of different ages, but how do you know that the age is different? How do you measure the age of these associations?
Ooh, that's a good question. Because determining ages of stars is actually not so easy. So I think for clusters, what you can do is isochrone fitting. So then you really need multiple stars in the cluster, and with an isochrone, which is basically the same age but different masses, you can see which one fits the best. So I think that is also, for example, how they determined the ages for at least some of these regions. There's many other methods also to determine ages. For example, if you just have one single star, I think it's difficult. I think maybe you can do it also based on the spectrum, but I'm assuming there will be large uncertainties. I think, for example, astroseismology is also a very good way to get precise ages, but then, of course, you also need your star to be pulsating and have this information. I also don't know exactly how this works, but I think there's multiple ways to determine ages, but it's in general not so easy to get precise ages.
Okay. In one of the picture of sphere that you showed today, not the IFS, but the wider field one, it's a small field, but we see a lot of background object, and this is something that is quite unusual in high contrast imaging to see so many.
Like this one, for example,
or even the previous one. Is it really specific to the? I think it was slide 22. That
this
one.
Yeah.
So this is something that we rarely see, right? And so I was wondering whether this is really specific to this star, or is it specific to this association, or is it specific to cluster of massive stars? Okay, can you comment on that?
It's sadly mostly specific to, well, in general, massive star clusters, but especially the Scorpius OU1 association, because this is really because the background contamination is so high. So we really had, for almost all of the stars in this sample, there were like many, around maybe on average 40 detections that we all had to characterize. Well, most of them are very likely just background sources. So I can understand why other people doing high contrast imaging don't look at these regions. But it's the regions where we are finding massive stars. So if we want to have enough statistics, we don't have a lot of other options.
Okay, then a question about sphere and high contrast imaging in general. What's limiting your performance with sphere? Because you want to go as close as possible to the star, but there are some limitations. So can you comment on that?
Yes. So there's actually multiple things that contribute to getting a high, your contrast as high as possible. So there's the adaptive optics correcting for the atmosphere of the Earth. There's the coronagraph blocking the light. And then there's how we process the data. So this principal component analysis, for example, and this angular differential imaging, which is also part of your observing strategy. But I think the most important part to get a good contrast, at least, especially very close to the central star, would be like a combination of this adaptive optics, also with the coronagraph, then being able to block this light well enough. Because, for example, we also had a lot of observations where the observing conditions were, for example, not ideal. So like really a very turbulent atmosphere, for example. And then you can see that we have a lot of light of the massive star still leaking outside of our coronagraph, likely pointing to the fact that this adaptive optics wasn't working in its best way.
Okay. So let's say we take this picture here. Obviously, when you have a picture like this, you measure the flux from the companion, right? So how do you go from the flux that you measure or the contrast with respect to the star to a mass estimate of the companion? Can you guide us through this?
Yes. So the flux that you measure from this image in the first place will actually be like a flux relative to the central star. Well, it's just in units that don't really have a meaning yet. And then we also get a separate observation of the massive star without a coronagraph, so that we can actually divide the flux of the companion by the flux of the massive star. And then we have basically a thing without units. And then we still have to multiply it with the flux of the massive star again, but then we can do it in a flux calibrated way. So a spectrum of the massive star where we do know the units, it can be an observed spectrum that's flux calibrated, but we usually don't have those. So therefore we use, for example, fast wind to create a model of the massive star, and then we multiply those, and that gives you in the end a flux calibrated spectrum of your companion. And then this you can directly compare with models. And in that way we get a mass.
Okay. Final question for me. It's about your the future, and you mentioned METIS already and the LT. So let's say you have access to the LT tomorrow. You can have the LT all for yourself for a night. Which of the association that you studied during your thesis would you focus on, and why?
Oh, that's a good question. I think if I have to choose one of the associations that we have, so either it would be the low density sample, because if we're using METIS, that also means that we will get better contrast than with sphere. And if we go to these massive star clusters, then we already have a lot of background contamination at the moment. This will only get worse. So that would be a reason to go for more low density regions of massive stars. Although I think the inner working angle of METIS will also be a lot better than what we have with sphere. I think if I calculate it correctly, it's even going to be 0.02 arc seconds. So that's really a factor 10 almost better. So in that way, I think it could also be interesting to, for example, look at the Carina region, because it's a bit further away. And we are missing now sources between, like, compared to, for example, Scorpio-1, between 250 AU up to around 400 AU. So I think probing this could also be very interesting. So yeah, I think one of the two could be nice.
Okay, that's all for me.
Hi, Tinne.
Hi.
Congratulations, and thank you for the very nice presentation. I have a question about how you think the systems will evolve further, given our current understanding of massive star evolution. For example, you can pick the ones with the brown dwarfs or the ones with 0.5, 0.6 solar masses. And how do you think will these systems survive? What will happen?
So as a massive star, evolves, for example. So these systems, the companions that we detect, they're very far away from the central star. So yeah, a couple of hundreds to thousands of AU. So I don't think these will ever like really start interacting with the central star, for example. So like no mass transfer or things like that. I think indeed it will more be a question of like, in the end, if the massive star is really evolved, may explode as a supernova, like what will happen to these sources? I think especially those brown dwarfs, the chances that they will stay bound are very, very, very low. I think they will probably be ejected.
Okay, thank you.
Any other questions?
Next, the committee members will discuss your defense and announce the result of deliberation. Yeah, thank you. And ladies and gentlemen, dear colleagues, I will now claim the result of the deliberation by the examination committee appointed for granting the doctoral degree in science, astronomy, and astrophysics. Tinne Pauwels has presented to the faculty the PhD thesis on the topic Companions of Massive Stars down to the substellar mass regime. In partial fulfillment of the requirements for the PhD in science, astronomy, and astrophysics, and Tinne Pauwels has defended his thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Tinne Pauwels the degree of Doctor in Science, Astronomy, and Astrophysics. Tinne? Yes, okay, thank you. Yeah. Okay. Tinne, by obtaining the doctoral degree, you commit yourself as a doctor to act also in the future in accordance with the basic principles of research integrity as described in the earlier European Code of Conduct: reliability, honesty, respect, and accountability. So, congratulations. And I close the session.
She doesn't have it.
Thank you. And the supervisor will give a speech.
Dear Dr. Pauwels, beste Tinne, it's a pleasure always to be the first to congratulate the new doctor and to congratulate you for your achievements today, certainly, but also in the last 4 years. So it's usually the moment where we want to look back a bit, but also look a bit to the future. So when I can't read what I wrote. Does that remind you of something, Tinne? So when we hired you, you'd done an excellent master thesis at the time that I think got you a prize. That was well deserved, and we wanted to keep you, but you had applied on a position on spectroscopy because that's the position for which we actually had funding at the moment. But at the same time, together with Madalena, you had written FWO project to do high contrast imaging, and that proposal was highly graded because they decided to give you the money to do this. So you've been here actually on your own money to do this project, and I've been very glad of it because otherwise we could not have had anyone to analyze all the data that you had analyzed. That was, I think, something very valuable. And the results that you had was not only doing the analysis of the data, because that's time consuming, it's also iterative, because each time you analyze that, it takes you a few days to do 1 star, and then you realize, oh, but I can do it better. And then you have to redo it again, and you do that, but when you have 100 stars, redoing it again is not easy, so you learn how to speed up your process, you learn how to automatize your tasks. And also for the last project, you learn a bit of statistics. That was also something that you were not so certain when we discussed about that, because it was a bit of an unknown field to you, a completely new approach, way more coding and code development than what you had done before. But still, you decided that you were going to do this. And so I wanted to say, I think, in an essence, that you're not necessarily afraid of a challenge, or maybe afraid is not the right word. You are afraid of a challenge, but you still do it. And this is maybe showing how much you've grown, because I think that maybe 5 years ago, before you started your master thesis, you would have seen the situation in a completely different angle, thinking that maybe you would not necessarily be up to the task, but you are. And so I think that is something that I want you to take away from this thesis, not only the beautiful science work that you've been doing that will outlast you time in here at the KU Leuven, but also the fact that you have realized that all of those difficult tasks, you are really something that you can do. So you're certainly some person of many talents. If I can mention a few, you have excellent qualities as a scientist. You're careful, you know what you're doing, and that's maybe the most important part of scientists. You also know when you don't know anymore. That's also a very important part. You have a science honesty. There's several times that you came up to my office and say, I think that we have a problem, while some people would not mention it or would hide it, and you were just completely honest about it. And that's the first step. If you want to solve a problem, you first need to know that you have a problem. And I think that's an excellent quality. There's other qualities. You've shown today that you have a talent for communication. I think we knew it, but this is clear that you have clearly demonstrated it. You have talents for art. That's for sure. You have knitting, karaoke. Maybe we'll get some dancing tonight. That I don't know. You got another prize. You've been elected as the best cupcake maker ever by my 10-year-old daughter. I think that you can be very proud of that, because she's an expert in the field. She was unfortunately not available to join the jury today, but otherwise she would have been doing that. All right, so I was thinking a bit about which kind of present to get you. And for some reason, I don't know how I had a bit more trouble with you than for other students. So first I thought about something about Stella cooking, something related stuff. But I just said, no, I'm not an expert in cooking. I will not make the right choice. So I was not as brave as you, and that was a challenge I decided not to take up. But I was on a fair this weekend, and I was walking through the stand, and there's something that caught my eye. So actually, it's on my bag, so I cannot show it to you. So the artist tell me that it was handmade and was unique, and that it was flowers. But when I saw what it was, I thought that it was not unique and that was not flowers. It was actually a plagiat of the cover of your thesis. So I thought that we should definitely sue the artist because the artist has been taking inspiration from the cover of your thesis. But the lady was really nice, and also, I mean, the lawyers and the suing people and everything's way too expensive. So I decided rather than to do that, I just buy the piece and I will offer it to you, and you will own the intellectual right of that piece. So you'll tell me later when I'll show you, and you can also quiz the audience, whether those are really flowers, or is it a supernova explosion, or is it where you see light echoes and around the clouds around it, or is that actually a massive star forming region where you have central massive stars and then maybe brown dwarf companions around it, or if this is just nice colors on a piece of paper, right? All right. Anyway, I hope that you can place that in a place where that you like. I hope it's not going to be a closet. I hope it's not going to be a water closet either, but in a place that you can see once in a while in your living room or wherever you like, where you can hang it and sit, and it reminds you of the good time you had during your PhD thesis, but also remind you of your many talents and the fact that you should never sell you short. There's many things you can do, and that's something that I'm confident in the next phase of your life, you will be successful, whatever choice you decide to make. I also want to give the floor to Madalena, that has been our joint captain in this adventure, and that we could not also have done it without the advice and guidance of Madalena.
Dear Dr. Pauwels, dear Tinne, I will be brief because I don't really like giving speeches, because Hook already talked a lot about a lot of nice anecdotes. But I have to say that we are here after a journey of more than 5 years for me, because maybe most of the people do not know, but everything started with a master thesis project that I proposed and to which you were assigned, and most likely it wasn't like your first and probably not even your second choice, but I think due to a still unexplained bug in the system, because I don't even think that the first choice was ever given to anyone that year, you ended up with the thesis with me. And sometimes I still remember this first like Zoom call, because it was COVID time, in which I tried to convince you that the project was not that bad after all. And somehow you stick to the project. I managed to convince you. But more importantly, you succeeded in everything else afterwards, because despite the difficult COVID times, I think we met maybe once in the entire year of master thesis. The fact that I went on maternity leave 15 days or 10 days before your defense, you still managed to write a thesis that was awarded like the prize for the best thesis in astronomy that year, and also to prepare the successful application that then led to this PhD. So really, the master thesis was just like the beginning of like this journey that brought you to today. There were many other challenges, but also a lot of like happy moments and successful things that happened on the way. And I think it has been a real pleasure to work with you. And in many times, you really challenged me and Hooks a lot. I still remember a question that you came to answer to us, to which I think we thought about for at least an hour. We couldn't find an answer. I don't remember it yet now, but I still know that it's, I don't know, somewhere in the back of my mind, and we still do not have answer to that question. But it was really like a pleasure to be challenged that way every single week. And also to watch you grow in confidence and as a researcher over the years. So thanks a lot to that bug in the system that allowed you to work with us, and thank you for trusting us in all these years and for the many things you have taught us along the way. And you may not yet know what the future holds for you, but if you were able to achieve so much out of a computer bug, just imagine how much more you will be able to accomplish next. So congratulations. And as a present, I went on the baking road, but just because I wanted to give you an Italian challenge, like to remember me in the coming years.
I guess now it's my time to say something. I haven't really thought about this a lot, but and maybe I can tell you some stories. So for Huuk, for example, I remember about 10 years ago, I was still a secondary school student, and we have this thing called Zuiddag. I think it's called Yuka Day now, but it's basically a day where, as a student, you go work for one day, and then the money that you earn goes to charity. And I was lucky enough to be able to work for one day at the Institute of Astronomy in KU Leuven. And it was actually Connie that mostly coordinated this. But I remember that the day started and we had all of these different talks from like scientists at the Institute. And then Connie introduced like, oh, we have this new professor at the Institute of Astronomy. And this new professor was talking about binaries. And I was immediately like, whoa, this is so cool. This is what I would like to do. And I only realized later, like this new professor at the time, 10 years ago, that was Huuk. So I think that's so cool that already in high school I thought like, oh, this is what I really want to do. And in the end, that's what I got to do with you. And I think it was great. I really, really enjoyed doing this PhD with you. Thanks for all your advice and your guidance, and also really always being so understanding on a personal level. So yeah, thank you for that. And Madalena, I'm also super happy with this lucky bug in the system that got me assigned to this master project in the first place. Because I also remember, indeed, at first I wasn't sure like whether I would like it, but I think there couldn't have been a project that I would have enjoyed more than this one. And also especially to be able to do it with you. And I think you're such a nice and kind person. And also you always, when I was a bit uncertain about something or giving a talk or doing something else, you always gave me so much confidence, like, oh no, you'll do great. And I think, yeah, it has really been a pleasure to work with you as well. So I have some gifts for you as well, of course, which I will give to you in a second. But I think there's not really any reason to keep anyone here from going to the reception. So I think, so the reception is in the Verbeekzaal. It's if you go back into the main building of Stuk, and then you take the stairs all the way up to the 6th floor. So, yes.